All right, folks, welcome to the 2.5 notes. Today we're going to be discussing distinguishing the differences between linear, quadratic, and exponential functions. So we're going to look at the equations, some graphs, some tables, and be able to tell which one is linear, quadratic, or exponential, or possibly neither. And then we're also going to be looking at some slope as well. So let's go ahead and get into it. This first part, identifying, should be mostly review. Because a lot of this I feel confident you guys know a lot of already. So we'll go ahead and get into it. So our first one here, classify each equation as linear, quadratic, or exponential. So this first equation, A, you can see it's 3x plus 2. This is mx plus b format, which tells us that that one is linear. If you look at B, we have 5 to the x power. Anything to the x power, so if you have a number like 5, and you have the exponent is x, again, the exponent is x, that's going to be an indication of an exponential function. So this one's exponential. The next one is just f of x equals 2. So 2, this would just be a straight line across the y-axis at 2. Another way of looking at it is it's essentially 0x plus 2. Still mx plus b, you just don't see this part. It's still, at the end of the day, linear. It's a straight line. D, again, you have 4 times 2 to the x power. Again, if x is the exponent, it is exponential. E, you have 7 times 0.25 to the 3x power. Again, if x is the exponent, it is exponential. One second. Sometimes when I try to use the eraser, it gets a little laggy. There you go. And then finally, you have f, which is y equals 4x squared plus 2x minus 1. The x squared is the giveaway that this one is quadratic. So quadratic will always have an x squared. It's not 2 to the x power, it's x to the second power, right? So it can be kind of similar to exponential because it has an exponent, but the x isn't the exponent here. It's 2. And so when the exponent is 2, that's quadratic. So key differences there. All right, similar idea with the graphs is what do they look like? So A, you can see we talked about exponential functions a lot last week. This is exponential again. You can tell by its shape, it's steep decline, and then it's leveling off on the x-axis. That's indicating exponential to me. B, this is a straight up line, so this one's linear. C is a lot like A, it's just upside down. And so therefore it's still exponential as well, for the same reasons as before. It's just upside down version of A. D can be a little tricky because it's a line, and a lot of people think it's linear. However, this is the only line in existence that is not going to be considered linear. That's a straight up and down line. A straight up and down line, this is going to actually be classified as neither, because a straight up and down line is classified as undefined. It's not linear. It is undefined. So if it had any slant to it at all, like B does, it'd be linear. But if it's straight, exactly straight up and down, it's the only case that it's not actually linear. So don't be fooled by that one. E, we have a U-shaped graph, which gives us a quadratic. F, another line, so linear. G is a kind of a squiggly line. This is actually a sine function. This is neither linear, exponential, or quadratic. It's actually considered to be a sine function. You know, sine, cosine, tangent, that stuff. A sine function is that what that one would be. And then H, again, very similar to A and C. This one is exponential as well. All right, now we're moving on to the tables. So here's how you can tell the tables apart. If the y values have a constant change, like you're subtracting 1 every time, or maybe you're adding 1 every time, but if it's adding or subtracting the same amount, it's going to be linear. If this one's interesting, the quadratic. The quadratics has a common second difference. So to identify these, you're going to take the difference of the first set of numbers. So 3 to 2 is minus 1, 2 to 3 is adding 1, 3 to 6 is adding 3, and 6 to 11 is adding 5. You're going to notice that all these differences are not the same. But if you take the differences of those differences, you're going to see that they are the same. So -1, +1 is an increase in 2. 1 to 3 is an increase in 2. 3 to 5 is an increase in 2. So they all have the same common second differences. So if that happens, it's a quadratic. So quadratic, you'll have to take the difference once and then again. And if it's the same on the second time, it's a quadratic. And then finally, we have exponential here. If you're multiplying or dividing by a common amount, that's going to be exponential. So you can see this one's multiplying by 3. If it was dividing by 3, it would still be exponential. So multiplying or dividing. All right. So let's look at these tables here. All right. So the first table, notice the differences in 7, 4, 1, -2, -5. We're seemingly subtracting 3. 7 to 4 is subtracting 3. 4 to 1 is subtracting 3. 1 and -2 is subtracting 3. 2, -5 is subtracting 3. All common first differences, making this one linear. B, we go 1.5 to 3, 3 to 6, 6 to 12. Careful that it's not an addition one here. This one is doubling, meaning it's multiplying by 2 every time. If it's multiplying by 2, this would mean that this one is exponential. C could be tricky because it doesn't, it could just be tricky. It could be a little deceiving. But if you look carefully, -9 to +9, that's an increase in 18. 9 to 27 is an increase in 18 as well. And 27 to 45 is an increase in 18 as well. So there's some big gaps there, but they're all the same, just like table A. So this one is, again, linear. Table D. So again, 6 to 3 to 2 to 3 to 6. It's not a multiplication one. It's a difference one. So let's look at it. 6 to 3 is subtracting 3. 3 to 2, subtracting 1. 2 to 3 is adding 1. And then 3 to 6 is adding 3. So it's not linear because these are not matching. But let's take the difference of these differences. So -3 to -1, that's an increase in 2. -1 to +1 is an increase in 2. 1 to 3 is an increase in 2. So a common set of second differences, this one is quadratic. E. So looking at the table, we go 16 to 8, 8 to 4, 4 to 2. You can tell these are being cut in half every time. This is multiplied by 1/2, making this one exponential. And then finally, table F, you can see 6 to 18, 18 to 54, 54 to 162. Big jumps there, which makes me think of multiplication. And yes, indeed it is. 6 times 3 is 18. 18 times 3 is 54. 54 times 3 is 162. This one's multiplying by 3, which makes this one also exponential. All right. So now we're going to fill in this chart and draw out this graph. So we have 3 different types of functions. The first one's linear. It's 2 times the x value, so 2 times the number we plug in. The middle one is x squared, a quadratic, so it's going to be whatever number we plug in squared. And then the third one is exponential, so 2 to the x power or 2 to whatever we plug in power. So let me fill these in. We have the first one. Let's zoom in a little bit. First one would be 2 times 0, which would be 0. Then we have 2 times 1, which is 2. 2 times 2, which is 4, and so on, right? 2 times 3, which is 6. So I'm just going to fill these in. Our second column, we have x squared, so this would be 0 squared, which is 0. 1 squared, which is 1. 2 squared, which is 4. 3 squared, which is 9. 4 squared, which is 16. And 5 squared, which is 25. And then finally, we have the exponential. So we have 2 to the 0 power, which is 1. 2 to the first power, which is 2. 2 to the second, which is 4. 2 to the third, which is 8. 2 to the fourth, which is 16. And 2 to the fifth, which is 32. All right, what I'm going to do off camera here for a second is just I'll graph these. So I have the points, like 0, 0, 1, 2, 2, 4, 3, 6, 4, 8, 5, 10, etc. I'm going to graph these 3, and then we'll come back and we'll look at it. So give me 1 second to put those graphs together. All right, so here are my graphs. They're not the best, but they get the job done. It's all those points graphed, and you can, of course, see I've color matched them. So now we're going to answer the 3 questions down here. Which function shows a constant rate of change in its y values? A constant rate of change is one that's consistent. It's not going to curve. It's just the same old slope, repeating itself, making a line, which is going to be our y equals 2x function, which is our linear function, the blue one. Its line is straight. So it has a constant slope. Question number 2 asks which function is largest between 1 and 2? How is it displayed on your graph? So my graph's not going to do a very good picture of this, but I think it's better illustrated really in the table. It's talking about the largest slope between points 1 and points 2. So if we look at points 1 and point 2 here, the blue function goes from 2 to 4, so an increase of 2. The middle function, red one, it goes from 1 to 4, which is increasing 3. And then the last function here in green goes from 2 to 4 as well. So the one with the largest slope is this middle function, this red one, because you're increasing 3 over this gap instead of just 2, like the blue function and the green function are. So the quadratic function here, the red one, is the one that has the largest change, largest growth between x values 1 and 2. Oh man, the handwriting looks awful, but it's difficult to write on this little screen. So I apologize for that. But it says the others have a slope of 2. Eventually, which type of function shows the most rapid growth in its y values? So this is the one with the steepest slope, which is going to be the green graph. As you can see, it kind of shoots upwards, and it's going to obviously do that a lot. And so that's an indication of the fact that it's going to have the most rapid growth because it's going from 16 to 32, whereas the other one only went from like 16 to 25. So it's going to have the steepest slope. It's going to increase the most. It's got to be that one. So y equals 2 to the x power, the exponential. It has the steepest slope. Is how we can tell that from the graph. All right, so now let's look at more things about slope. So let's consider the following equations, right? As x increases, will the value of f of x always be greater than the value of g of x? Will an exponential function eventually always exceed a quadratic function? So let's fill in the chart. Same as before, just kind of plugging in the numbers and completing the table. So we're going to do the f of x. So 5x squared plus 4. So we're going to plug in 0. So that would be 5 times 0 squared plus 4. And if we plug in 0, this would come out to 4. If we plug in 1, let's see, 5 times 1 squared plus 4. 5 times 1 squared plus 4, that would be 5, that would be 9. If we plugged in 2, we'd get 24. I'm gonna grab a calculator real quick and finish writing these in, so give me 1 second. Okay, so I know I paused that for a second, it didn't seem like it, but I did. If you plug in 3, you're gonna get 49. If you plugged in 4, you're gonna get 84. And I'll just keep filling these in. It'd be 129, 184, 249, 324, 409, and the last one, 504. All right, so now if we do the same thing with the other function, which is 2 to the x power. So 2 to the 0 power is 1, 2 to the first is 2, 2 to the second is 4, and so on. This would be 8, 16, 32, 64, 128, 256, 5, 16, 1024. All right, so as x increases, will the value of f of x always be greater than the value of g of x? So will the blue one always be greater than the red one? As you can see, it definitely starts that way. 4 is bigger than 1, 9 is bigger than 2, 24 is bigger than 4, 49 is bigger than 8, and so on. But it doesn't stay that way, because at the end here, you can see that the blue one is actually less than the red one. 409 is smaller than 516, 504 is smaller than 1024. So the answer is no. G of x catches up and passes. May as well catches, ES, catches up and passes. Will an exponential function eventually always succeed a quadratic? Key here is always, and the answer is yes, actually. Exponential will, yes. Exponential will, yes it will. I'll just say yes it will. Kind of explains it in those sentences there, so yes it will. All right, scenario 3. Will the growth rate of g of x ever exceed the growth rate of f of x? All right, so let's put these together. So we have f of x, which is linear. Again, I'm going to go ahead and fill this table in and draw out the graph so we can talk about it. So give me 1 second. All right, so I decided I didn't want to do the graph. The graph's going to just take a lot of time. So we can really see everything we need to see from the table though anyway. Will the growth rate of g of x ever exceed the growth rate of f of x? So g of x compared to f of x. As you can see, g of x starts off smaller, right, than f of x. -1 is smaller than 7, 1.5 is smaller than 9, and so on. But yes, it does pass. You can see here they're both 15, but then g of x is greater than f of x after, from 7 on down, 7, 8, 9, 10. The g of x is higher than the f of x. So yes, I would say after x equals 6. Will the growth rate of h of x ever exceed the growth rate of f of x? So again, the answer is yes, because you can see at 7, they're about the same, 17 to 17.1. But after 7, the h of x is larger. So yes, after x equals 7. And will the growth rate of h of x ever exceed the growth rate of g of x? H of x, again, as you can see, it's actually larger to begin with, but then it becomes smaller, right? You can see it's now smaller than g of x, but then it passes it again. So yes, you can see at the end that h of x is larger than g of x. So yes. All right. So the graph and tables of a function increasing. So basically what's going to happen is exponential functions, so exponential, will always eventually exceed a function increasing. I don't know how I want to say this. Increasing, I guess, linearly or quadratically. I don't know if that's a word, but that's always true. Exponential will always eventually exceed both linear and quadratic is pretty much what we're going to say there. All right, I'll leave it at this for now. There's a few other questions that we can answer in class, but I'm going to leave it at this because I think we've covered the main points. There is some other stuff about slope that we're going to cover in class, so be mindful about that. But yeah, I'll see you guys then, and best of luck on the skill check. Bye for now.